So let's play that game where we're testing the sound. Are you on the Zoom, Elizabeth? Okay.
So you're doing a PowerPoint again?
Maybe I'll probably do PowerPoints for the rest of the semester, but they may not figure out just find out. And it's not the issue with Blackboard.
Okay, so I don't need my camera then.
Probably only need one.
They'll be quick.
I may not need any.
So are you
I'd
saying,
probably still like to have one.
are you saying that you don't?
Well,
Is that what you're telling me?
I'll go back to the
Yes.
Is
It's almost there. So Mr. Snacks is at the vet this morning, so I might have to run out with the phone call, just so you know.
me, everyone can be here.
Let's see.
I'm sure you can hear me in the room. There's no reverb. We might actually be getting this right. That's better.
Yeah, that's very embarrassing. That's really no, don't hear that. I was like to myself. I know, my laugh is not something I ever want to hear.
We all call it a cackle, but
No, actually, my family does call it cackle. I wish cackle.
So I put online a handout for today. It was on fluid statics. I did print some out, but I didn't bring them. So we probably will not get to that handout until the end of today's lecture. And we will use that handout next lecture as well. And no big surprise, almost everything in the handouts I give you is in your textbook. So it's just a different way of packaging it. Starting off, are there any questions from last time? Okay, so I want to continue with what we were doing last time, and that was fluid statics. And before that, while I have your attention, I'm probably going to stop giving this announcement. You should expect a homework every class, maybe two. And it's just one problem. Why is that not projecting? Oh, I know why. You have to share a screen. I'll get it. So again, as I was saying, now all of a sudden we're getting feedback.
No, that was because mine wasn't muted.
All right. So now we're not seeing. Can the people online see my screen?
Yes, I can.
Good. The people in the classroom can't. That's the problem. It says it's projecting in the back and not in the front. Isn't that wonderful? Well, unfortunately for those in the room, you may have to look at the back of the room. I'm not seeing why this is not firing up both the screen.
I think the other professor had that problem because they were, I think the other professor had that problem because they were looking at the back of the room.
Oh boy, okay, so that is projecting light. So the projector is sending light on this, it's just not showing up. That's what's bizarre. All right, so yet, once again, when we thought we had everything conquered, to X all day. All right, so what we did last time was to develop fluid statics. And if you want to move your seat closer to the back of the room, I don't blame you. And for fluid statics, remember, we took a coupon, a little, yeah.
I guess there should be no problem. The students inside the chat room can see the board. I guess
Yeah,
it's better to guess.
in the chat room, they should be able to see it on Zoom.
Ah, yeah, yeah.
Yeah, they should be able to see it on Zoom. It's not an issue. Okay, so we took the coupon, we distributed pressure around it, we assumed pressure varied in space, and what we found when we went through that analysis was for the static fluid, there is no change in pressure moving horizontally. The time we change pressure is when we move vertically. Originally, we started with the XY horizontal, Z vertically upwards. And for that context, if we move into Z, the proportionality or the rate of change or the pressure gradient is equal to the negative of the specific weight of the fluid minus gamma, or that's minus density times acceleration due to gravity. So again, that's started with partial differentials. That then becomes ordinary differential because pressure is only a function of moving in the vertical direction. And when we do an open integration from two completely random points in the fluid continuum, we integrate that dp dz is equal to minus gamma by separating variables and integrating between the 2 points 1 and 2. And you either get this first equation that we played around with last time, the difference in pressure, P2 minus P1, is equal to gamma Z1 minus Z2. Notice the negative sign is gone because I switched the position of Z1 and Z2. Okay, so everything is consistent. It would also equal, if we wanted to, what you're used to seeing, equal cancel minus gamma Z2 minus Z1. So that's the only difference between what we did before. The other thing we could do is group like variables. And so the second line here, you can see where we've grouped like variables. And then the third thing you can do, I mean, we're having so much fun with this equation, is divide everything by the specific weight of the fluid. Because again, right now we assume that the specific weight is a constant. We'll relax that a little bit later. And I want you to look at the three equations on this page. Mental exercise. What are the dimensions on the left-hand side? What are the dimensions on the left-hand side? They're pressures. P stands for pressure. That's length per time, force per length squared. Force per length squared. That's an FLT system of units when you see F, force. Pounds per square foot, Newton per meter squared, which is a Pascal. What are the units on the right-hand side? They must be the same. There's no option. This is an equation. So specific weight has the dimensions of force per length cubed. You're multiplying the specific weight times the length, which gives you force per length squared. Look at the second equation. What are the dimensions on the left-hand side? There's still pressure, right? And they're the dimensions of each and every term in that equation. When we go to the third equation, we've divided everything by specific weight. So on the left-hand side, you have P1 over gamma plus Z. Let's take the easy one. What are the dimensions of Z? Length, right? And therefore, everything in this equation, because it's always been dimensionally consistent, everything in this equation has the dimensions of length. P over gamma has the dimensions of length. If you think about it, pressure is force per length squared. Let's put it up here. Divided by force per length cubed. And that gives you the dimensions of length. And so what this is fundamentally saying to you is that you can represent a pressure by a column of fluid. Conversely, you can represent a column of fluid by a pressure. And it's very, very commonly done. We already did it with the barometer, and you've heard that forever. The mercury's at 29 inches, for example. You're representing the atmospheric pressure as a column of mercury in this case, a column of air to a column of mercury in this case. But equally, we could say that local atmospheric is 14.7 psi. Now we're actually using the pressure. And so we mix and match this all the time, and you've heard it very, very often. So the other thing we talked about last time was we, in many problems, have a free surface, not only in this course, but when you leave here. And whenever you see a free surface, you want to take advantage of it. The last equations we were talking about, the 3 on the previous slide, had 5 variables. And the only way we can solve it is to know 4 of them. And whenever you see a free surface, we can employ that free surface to get rid of 2 of the variables. We can, 1, recognize that we have atmospheric pressure there because that is the definition of a free surface, location where you have atmospheric pressure, whether it's above the ground or below the ground. So the groundwater table is a free surface. And the other thing we can do at the free surface is set our elevation data right there. So whether we're using the z-axis positive up or the h-axis positive down, that's where we can set h or z equal to 0. If we're using the z-axis, as we go down into the fluid of interest, z is decreasing. If we're using the h form of the equation, as we go down into the fluid, not only is pressure increasing, but h is increasing. That's why the h-axis is a little more convenient. So again, what we have is this free surface. And remember, that triangle with the 1, 2, or 3 lines under it just indicates an interface. Not all interfaces are free surfaces. Free surface has a very specific characteristic of atmospheric pressure. So again, the h-axis is positive down. And as we move down into the fluid, we would see pressure increasing, as I've indicated on the right-hand side of this diagram. And at any particular location, h below the surface, when we integrate any of the equations on the previous slide, the pressure anywhere below a free surface is simply the specific weight of the fluid times h below the free surface. P is equal to gamma h. So with all those partial differential equations we used all this week and the extended form of the equations on the last slide, if you have a free surface, fluid statics boils down to a very, very simple equation to use. But this P is equal to gamma H is still saying you can either represent a pressure as a pressure, P, or you can represent the pressure as a column of fluid, P over gamma is equal to H. So again, this is what I just talked about. Instead of using dP dz equal to minus gamma, where z was positive upwards, h is positive downwards, and now dP dH is just equal to gamma. And when we integrate that ordinary differential equation from a free surface, we get P is equal to gamma h. Pretty straightforward. So I was asked this last time, and I said we would get to that later. Now is later. So what if you did have variable density or specific weight as you move through the vertical, whether it's z or h dimension? And that either happens in gases over large distances, say the atmosphere, and it also happens in liquids over large distances, say the ocean. And so in this case, what's happening is once you start going over larger distances, the bulk modulus of elasticity and the fact that the fluid can compress is starting to operate. And that the deeper and deeper you go in the ocean, you have P is equal to gamma H. You have more pressure at that location, and you are basically squishing the fluid. That's what happens in aquifer systems as well. So if the density or the specific weight were not constant, what would happen is when we separated variables and integrated the expression, we pulled specific weight or density out of the integration because we said it was constant. In this case, now you can't. You have to just leave it in the integration and then include it when you do the integration. So again, we started and developed partial derivative of P with respect to partial derivative Z. We started that because we thought that pressure varied with X, Y, and Z. We found that it's only varying with Z, so that allowed us to go to the ordinary differential, dP dZ, which was equal to minus gamma. And then what we did was separate variables, dP is equal to minus gamma dZ, and then we wanted to integrate. But you see the very last term in this sentence is, instead of minus gamma dZ, I say minus gamma of Z. So now what we're saying is the specific weight or the density is also a function of Z. That's what gamma of Z means. That specific weight or density is a function of movement in the Z direction. It's a compressible fluid. And so now when we perform the integration, we have to leave, remember, gamma is equal to rho g. Specific weight is equal to density times acceleration due to gravity. So whatever I'm saying about specific weight gamma, equally we can say it about density. Half dozen, 1/6 of the other. So now what you see is we can integrate this expression, whether we're integrating with respect to gamma or integrating it with respect to density. The issue is you need to know what that function is, gamma of Z or rho of Z. You need to know what it is, or you need to take data such that you could tease out from the data what that function is. And for a lot of fluids, we actually know this. This is nothing new. But you do the same thing as you do before. Now that you've separated variables, just perform an open integration between any 2 points in the continuum. And the left-hand side, question?
Yeah. I have a question that says, what is the difference between dP dZ and the partial dP over partial dZ?
So that came when we assumed we were using partial derivatives because we assumed pressure varied in all directions. What we found was that pressure didn't vary in the X and the Y. And so pressure only varies in the Z, and so it's a partial derivative because pressure isn't varying with the X and the Y. That's why it goes to an ordinary differential. And if that didn't clear it up, they can certainly ask me, but then I demand to know who they had for calculus because I will go over and slap that person.
Okay.
So on the line we were at, we separate variables. And on the left-hand side, the integral of dP from point 1 to point 2, where you have P1 and P2, is just P2 minus P1. That's the same thing we had before. On the right-hand side, what we're doing is integrating this specific weight or density function, gamma of Z dZ, from Z1 to Z2, the 2 points where we're trying to get the pressures. And what we're just saying is that the integral of gamma of Z, gamma is the lowercase of the letter, and this upside down looking L is uppercase gamma. So all we're saying is that uppercase gamma is the integrated function. So for example, if I had the integral of x dx, that would equal to 1/2 x squared, right? So this is gamma of, don't ask me what I did, but I did it. This is gamma of Z analogy, and this is gamma of Z, the integrated form. Like me writing down in the corner. So I'm going to do this in a more numerical example, but here we have, for example, a fluid where you can see the z-axis and you can see the horizontal axis is the specific weight axis, gamma. That's what the horizontal axis is, gamma. And what you see as you move down into the fluid, the specific weight is increasing, and it increases as some basic specific weight, gamma 0, and as you move down into the fluid, it's increasing by some constant times the location, z squared, where z is measured to the free surface. So you can see this is a nonlinear function, and all it's saying is that as you move through the fluid, the specific weight and the density are not constant. And again, if you know this function, and again, for most fluids we know this, that's where we would put this function before we were calling this gamma of z on the previous slides. So there's that function from the previous slide, gamma of 0 plus kz squared. And we're performing the same integration that we did before between points z1 and z2. So if I just said, what's the integral of gamma 0 dz? Gamma 0 is a constant, so that would just give you gamma 0 z, right? And the other would be, what's the integral of kz squared dz? That should be k over 3z cubed, right? So when we integrate the equation above, that should be a subscript.
We have another question.
Question.
Why does the upper and lower bounds of the middle integral swap?
Because I screwed up. Okay. Those should be as they were over here. It's actually, that's the correct pair.
Okay.
This is the correct pair. It's the same as that one. So that's Z2 and Z1. And I've said this before in here, I'll continue to say it. I never hold you for derivations, just the end results. In this case, I'm just trying to get you to understand that we can certainly attack fluids in which compressibility is an issue. So when we integrate this equation down below, what we were calling capital gamma of z is found within this integral. So if we know z1 and z2, so this is integrated from z1 to z2. If we know z1 and z2, we can either find the pressure difference or knowing the pressure at one location, again, knowing z1 and z2, we can calculate with change in pressure.
Yeah. What is the where does the negative come from on the integral?
Way back when, dp/dz was minus gamma. That's on the previous slide. And all we did was take that exact same equation, and it already had the negative in it. So that's probably where I'm going to leave this example. If you have a problem here or when you leave here, you know, you could be working in marine systems and you're putting something under the North Sea, and you're the structural engineer looking at the 1,000-foot tower that you're putting out there, and you're going to have to worry about the pressures on the bottom. You're going to have to worry about this. Or you just hire, you know, coastal engineer. So this is the next slide. And the equation at the very top is, again, the one we integrated and found. And again, if we started at a free surface, you can start to knock out some of these items. So if point 1 was the free surface and point 2 is somewhere below the free surface, then this would be the analogy to P is equal to gamma H. It's a lot more complicated because you had to account for the fact that the fluid was compressible. And again, I say Z2 is less than 0. Why? Because from the free surface, we put the elevation datum where Z is equal to 0 at the free surface. So as you move down into the fluid, you're going into a direction of decreasing Z, decreasing Z2. If we had used the H-axis, I show you the equation down below. So having a compressible fluid is not the big issue. The biggest issue is finding the equation that describes how the specific weight or the density changes with depth into a fluid. So again, I post these all afterwards. I know a lot of you are writing feverishly, but the important thing is the concept. This concept of dP dz is equal to minus gamma. And the one that I'm not writing, dP dx and dP dy are 0. The only places we're getting pressure changes is when we move vertically. There's no pressure change when you move horizontally. I would say the vast majority of the engineering applications we have a constant density or a constant specific weight fluid. So again, what I've just showed you is a very small percentage of the problems you would ever run into. So you have already seen in some of the labs how we can represent pressures as a column of fluid. So for example, this fluid, if we put a Bourdon gauge here, might read, for example, 3 psi. At that same location, we could equate that pressure to some column of fluid. So instead of 3 psi, we may say that's equal to 1.2 feet of some fluid. And in the lab, what you will see is we can actually be plotting how the pressures change as you move through the system. And you're actually going to be doing that in the latter part of this semester, both in the lab and both in homeworks and probably on the exam, where we're looking at how pressures are changing. And just to give you a preview, if you look at what's happening in this pipeline, what happens is you have a large cross-sectional area and it's going into a smaller cross-sectional area. And as we'll see from continuity, that means the velocity goes up. Somebody had to pay the price for that. And who paid the price in the horizontal pipeline is the pressure. And so what happened in that constriction was the pressure went down. You have probably done this in your own experience. I've a few times used the analogy of where you have the garden hose flowing. And instead of going over and shutting it off at the faucet, you just stay at the hose and you crimp it. And where you crimp it, you start hearing it hissing. What's happening is, yes, you've slowed down the flow, but the velocity through that crimped area is so high, the pressure went down below the vapor pressure. So this happens in engineering applications everywhere, and we just need to understand it. And in fact, we design around these conditions. All right, what we're going to jump into now, and maybe for the rest of the lecture actually, is looking at when we have multiple fluids. And when we have multiple fluids, remember the whole derivation for fluid statics so far has been for a fluid continuum. Now we're going to have multiple immiscible fluids, and so you have a discontinuum, yet you have a piecewise continuum in each and every fluid. So for example, here you see on the left-hand side, fluid with density rho 1 and fluid with density rho 2. And what would happen is if you only looked at fluid 1, you would see that if H is equal to 0 here, so here's the H axis and here's where H is equal to 0. As we move down into fluid 1, P is equal to gamma H1. From that free surface, nothing new, no revelation. But at distance L1, we go from fluid rho 1, density 1, to fluid rho 2, density 2. And rho 1 is less than rho 2. That's why rho 2 sits on the bottom. It's a denser, heavier fluid, immiscible, like gasoline floating on top of water. Specific weight of gasoline is around 0.7. Specific gravity of water. Specific gravity of gasoline is around 0.7. Specific gravity of water is 1. So what would happen is, at the interface, we know in fluid 1 we have pressure there, gamma 1H. In fluid 2, right at that same location, you have the same pressure. As you move further down into fluid 2 in this direction, the pressure, you can see the profile of the pressure distribution takes a marked increase in slope. And that's because the specific weight of fluid 2 and the density of fluid 2 are higher. Remember, dP dz is minus gamma. So when we went from fluid 1 to fluid 2, we went to a larger value of gamma. And that's why you see the slope change. And what it says is, for a unit distance in fluid 1, we had a unit pressure increase, delta P. And for that same unit of distance in fluid 2, you have a larger pressure increase for the same change in delta Z, because again, it's a larger specific weight fluid. And so the pressure distribution down below, you would start at the pressure, that should be a subscript, gamma 1 L1. That's the pressure you started at, and as you continue moving down into fluid 2, it should be gamma 2 times H minus L1. I don't know how that got chalky. So we can describe the pressure distribution down below as the starting pressure at the top of fluid 2 is gamma 1 L1. And L1 is the distance, that the total depth of fluid 1. And then as we continue to move down into fluid 2, it would be the distance we're moving into fluid 2, which is the total distance H minus L1, the distance through fluid 1. So H minus L1 is the distance you're moving through fluid 2. And gamma 2 times H minus L1, gamma 2 times H minus L1, which is that second term, is the change in pressure as you move down into fluid 2. And then you would add that to, again, the pressure at the very top. So again, this piecewise continuum is just applying the law of fluid statics in a piecewise fashion as we move from fluid to fluid to fluid. And you're going to see more of this. This is just introductory right now. So this gets us into manometry. And all a manometer is some type of a device that employs fluids or lengths of fluids to determine pressure or pressure differences. So here you can see 3 different manometers. And if this first manometer is just a U-tube, question?
Yeah, on the last slide, was L also depth?
L is L1 or L2. L1 is not depth measured on the H-axis. L is the finite thickness of the fluid, either fluid 1, L1, fluid 2, L2.
So it's the depth for each individual liquid.
Is the thickness of the liquid. I wouldn't call it a depth. So on the left side manometer, you know from a long time ago this saying, water seeks its own level. In fact, there are water levels that people use. They'll use hoses to level things when you don't have any other mechanical devices. And all this is saying is, water seeks its own level. It just says dP dx is 0. So again, I went through all this rigorous calculus to tell you something you already know. However, think or ponder if these were either vessels, that's what these bubbles are on the top, or a process. And in one process, we have pressure P1, and in the other process, we have pressure P2. And in this case, they both happen to be exactly the same. You would expect to see the fluid level on the manometer in this case to be the exact same, right? Let's do the same thing now, only we increase the pressure of P1 over the pressure of P2. What would you expect to happen? Well, if you increase the pressure on the left-hand side, you would expect the meniscus on the left-hand side to go down and the meniscus on the right-hand side to go up. And that's what you see. This distance is known as the manometer deflection. Okay, and if it goes down L on the left-hand side and you have a constant diameter tube, then it went up L on the other side. So when they want to get tricky in problems, whether in this course in your book or on the FE exam, they'll have different diameters on either side. And then you don't get the same rise and change on each side. But when it's a constant, you should have the same change on one side as the other. And then conversely, in the third manometer setup, what we've done is increase the pressure on P2, or another way of looking at that is we put a vacuum or we decrease the pressure at P1. You don't always think of one pressure increasing. It could be certainly one pressure decreasing. And again, look at what the liquid level does in the manometer. And that's going to be the key to helping you understand your answers. Because you can go through the calculations and maybe get a negative or a positive number. But at the end of the day, you have to be able to ask yourself, does this look realistic? And so in many of these manometer problems, just look at the change in the meniscus. For example, look at 3. What would have to be the relative pressures P2 and P1 to get the manometer levels to look like that? You would have to have P2 greater than P1 for that to happen. Do you understand that? Because again, you can get overly complicated in these systems. So I'm going to start just not theoretically, but applying fluid statics to a more complex manometer. This is known as a differential manometer. So what you see on this diagram, M and N, they could be cross sections of the same pipe. They could be miles apart, they could be feet apart. They could be, M and M could be cross sections of 2 different pipes. M and N could be huge tanks. Okay, so they're just schematic as, I call them pressure vessels. They're a location where we want to know the pressure. M or N could just be the atmosphere. And the tube is just open to the atmosphere. But again, schematically, we can just call it some kind of pressure vessel. It's a location we either know or we want to know the pressure. So with a manometer, what happens is we have some pressure PM and we have some pressure PM. And then the fluids here you see fluid A is not only where M is located, but fluid A continues up until you hit the manometer fluid, fluid C. And then in pressure vessel N, we have fluid B, and again, that continues through here. And then the manometer deflection in this case is the distance I'm drawing. So in this complicated sense, just focus on fluid C. Just focus on fluid C, the manometer fluid. Just looking at that fluid and how it deflected, which pressure do you think is greater, PM or PN? PM, right? So again, when you get an answer, you should be able to do this very simple question. Did my answer reflect that? So, some guidance on manometer problems. And again, not all of them are as complex as the problem I just showed you. Manometer problems, attack the problems as a piecewise continuum, just like I was talking about earlier where we had fluid row 1 and row 2. Start at one side of the manometer and then work your way through with fluid statics. And when I say working through with using fluid statics, you're using two things we developed. dpdx is 0 and dpdz is minus gamma. That's what you're using. We typically ignore any capillarity effects, so we just assume that all the interfaces are level. In a rare problem where you have very small tube diameters, capillarity may be an issue. And in some problems in the FE or here, they actually make that part of the problem. And then always take advantage of dpdx is equal to 0. So we're going to look at the same capillary system. And you'll see that on this one, let me see if I can bring this down a little bit. Just want to bring it down so you can see it. There we go. So here's our differential manometer, and what you'll see is I bothered to make some definitions. So HA is from the center of pressure vessel M to the interface between fluid A and fluid C. HC is what I call the manometer deflection, and HB is the distance from the center of the pressure vessel N to the meniscus between fluid B and fluid A. And the guidance I gave to you on the last slide was start at one side. So for example, we're going to start here where we have PM. And I'm going to ask a very, very difficult question. Pay attention. If I have PM at the center of this pressure vessel, and I go horizontally over to here, what pressure do I have? PM. dpdx is 0, right? That wasn't so bad. Do I have a continuum as I move up into the left side of this manometer? Yes. Is it the same fluid as I round the corner and go down to the other side of the manometer? Yes. So I want to find the pressure at the fluid A, fluid C meniscus. So basically, I'm starting at this elevation, and I'm going up to this elevation. And I want to know the pressure here. And I'm going to call that AC, PAC. It's the pressure right at the fluid A, fluid C meniscus. We started at PM, and our z-axis is that way. And when we increase pressures, if we move down in a fluid, we increase pressures. If we move up in a fluid, we decrease pressure. So, relative elevation from this elevation, I'll call ZM, to this elevation, ZAC. Did I move up in the fluid or down in the fluid? Did pressure increase or decrease? It should decrease, right? That's the decreasing pressure direction. How much did the pressure decrease? Well, we started at PM, and the pressure, I moved through fluid gamma A, and I went a distance of HA. That would be the pressure at AC. Everybody online should ask me a question now, or anybody in the class. If you don't understand this, what I'm trying to do is start at one side, M, and go to the other side, N. In manometer problems, the questions are either find one of the pressures in the pressure vessels, PM or PN, or find one of the fluid measurements, for example, the manometer deflection, Or in a bizarre question, they could be asking you, what's fluid density A, B, or C? The same equation will answer all of these. And that's why I'm guiding you, start at one side and just move to the other. Somewhere in the final equation is your answer. Question?
So, PM is the pressure of fluid A at M.
So PAC, I didn't hear,
Sorry, PM is
Yes.
the pressure of fluid M, or fluid A.
PM is the pressure at location M.
Okay,
PM is at the center of that pressure vessel.
so that is different than saying it's the pressure of fluid A, like that pressure
Well,
changes.
A has different pressures. So A has a pressure here, and it has a pressure here, and it has a pressure here. If you're moving vertically, the pressure in fluid A will change. So it depends on where you're talking about it. But throughout, all those points I pointed are all in A. And so I started at M, and I moved through A to get to the AC meniscus, the ACL meniscus. And all I want to do now is I want to know the pressure where fluid A meets fluid C. Why? Because I'm moving through this manometer to get to the other side.
And the only thing that affects it is the change in the Y.
dP dZ is equal to minus gamma. It's not necessarily water, it's any liquid,
Right.
any gas. So in this case, I know the fluid at the pressure at that interface based on, for example, knowing PM, knowing specific weight A, and knowing the distance HA, or all the elevations. So we're not done yet. We ultimately want to get over to N. That's the goal. Go from one side of the manometer to the other. Can I go from where we just said PAC horizontally over through the manometer? One, am I in a continuum? So the point on the left was at the AC interface. The pressure in fluid A and the pressure in fluid C are the same right at that interface. Just as we did as the fluid continuum example, piecewise continuum example a few slides back. So now we're moving through fluid C like this, and we're just getting to a point horizontally over. dP dx is 0. That's PAC. It's what we just calculated. Okay? And we're trying to go through. We're trying to go over to M. But because we have different fluids, all we can do is go up to this location. And let's call that not PCB, I don't think you'd like that, PBC. Okay, so that's the pressure at the fluid B, fluid C interface. How would I calculate the pressure at PBC? Well, we started at PAC, and we moved through fluid C upwards a distance of the manometer deflection, HC. Did pressures increase or decrease by moving upwards in the fluid C? Decrease. Whenever you go up in a fluid, you're decreasing pressure. So in this case, we started at PAC, and we went up through fluid gamma C, a distance of HC, and that's PBC. Or we could substitute what we found before for PAC, and we would find PM minus gamma A HA minus gamma C HC is PBC. So now what we have is the pressure at the fluid C, fluid B interface. The pressure at that location is the same in both fluids at the interface. And so if I went from that point horizontally over, that's also PBC, but now I'm in fluid B. And now what we have to do is go down a distance HB to get to that location. So if you look at the bottom of your page, what you see is we started at PM. We started at PM. Then we subtracted gamma AHA to get to the pressure at the fluid A, fluid C interface. We then went across the manometer and it went up fluid C to get the pressure at the interface between fluid C and fluid B. And then when we went from that interface horizontally over, we stay in fluid B, we went down from that location to the center of pressure vessel N. And so we increased, that's why we added gamma BHB. And at that point, that's equal to PM. So again, in that equation in the bottom, there are a lot of variables you would either need to know or be able to figure out. You can only use that equation to solve for one unknown. So that's generically how you would go through manometer problems. This is a complex one, I admit that. I'm going to do an example with a much simpler setup, but we're using the same principles. We're just representing pressures as columns of fluids. So we're going to have something called a benzene evaporator. So basically what you have is this pressure vessel, and we're going to call that pressure vessel A. And at the center of that pressure vessel, that's what we're going to focus on as our starting point. And again, the blue fluid is benzene. Highly flammable, no matches, please. And then what you see is the U-tube. Focus on the tube. Focus just on the tube. The tube is open to the atmosphere on the right. Look at the fluid level of the benzene. What would cause that fluid to deflect such that the benzene didn't seek its own level? What would push down the fluid on the right? Either the atmospheric pressure is, well, either way, the atmospheric pressure on the right must be higher than whatever pressure is in the vessel to bring that down. Otherwise, the benzene would seek its own level. So you know that PA should be something less than atmospheric. In a gauge pressure datum, that would be a negative pressure. In an absolute pressure measurement datum, it's some positive pressure, but that positive number is less than local atmospheric pressure. So let's say the pressure measurement, the manometer deflection from the center line of the pressure vessel to the air benzene interface is H, and that's 10.6 centimeters. The question is, what's the pressure at A? So here's the specific weight of benzene. This is the specific gravity of benzene. Specific gravity is dimensionless. From the specific gravity of benzene, we know that the specific weight of benzene is equal to the specific gravity of benzene times the specific weight of water. So that allows us to calculate the specific weight of benzene. And then what just came up was, again, that tube on the right is open to the atmosphere. So we have atmospheric pressure on the right. So here's our setup. We're going to start at the interface on the right-hand side. We're starting over here. So what's the pressure here where I'm making all the dots? What's the pressure there? Outside the entire system. Atmospheric pressure, right? What's the pressure right there at the top of the tube? Is it a continuum? It's atmospheric pressure, right? It's a gas. So all the way down to there, you have air. And again, when we look at gases compared to liquids, the change in pressure in the gas is negligible. So we assume that the pressure outside of the system is the same right at that interface. So we know the pressure there. We're going to start at that location at point A. And what we would say is, we know the pressure at A is atmospheric. That is the same pressure not only at the air at the interface on the right, but it's the pressure of the benzene on the right. So if I move through the benzene right to the same elevation, the pressure in the benzene on the left-hand side of the tube at the same elevation of the interface is atmospheric. We increase pressure by going down, and we decrease pressure going back up. But now I want to continue going back up to get to point A. And if we go from the atmospheric pressure at this location, we are going in a decreasing pressure direction, and so the pressure is going to decrease as the specific weight of benzene times the manometer deflection. That gets us to this location. This is what minus gamma BH gives us. It gives us the change in pressure between these two locations. And so P atmospheric minus gamma BH is the pressure at A, and that's what we were after. So if we work this problem in gauge pressure data, atmospheric pressure is 0 Newton per meter squared. Specific weight we just calculated, and then again, we were told that the deflection was 10.6 centimeters, which is 0.106 meters. And so the pressure would be minus 903 Newton per meter squared. Again, it has to be less than atmospheric. If we work this problem in absolute pressure, instead of the 0 Newton per meter squared, we might use 101,000 Newton meter per squared absolute. And then we get a positive number for PA, but it's still less than atmospheric pressure. So again, you can always work problems in absolute or gauge. Just don't mix or match. So that's what I just said. So I'm going to end today's lecture here because I'm already over and it's Friday. New labs are due. Don't yell at me. And expect to see homework, but have a pleasant weekend. Be healthy.
You'll be there.